I'd like to welcome everyone and thank you for joining us this morning. Our webinar today is going to be on improving the environmental sustainability of concrete through material efficiency. My name is Mike Centetos. I'm the Policy Director for the National Center for Sustainable Transportation. I'll be moderating the webinar today. Before we get started, I'm just going to do a quick introduction, let you know who we are. This is part of our quasi-monthly webinar series that we sponsor here at the National Center for Sustainable Transportation. We're part of the University Transportation Centers program administered through the U.S. Department of Transportation, and we're a consortium of 6 universities from around the country focused on advancing environmentally sustainable transportation through cutting-edge research, direct policy engagement, and education of our future leaders. Today's webinar is going to last 1 hour. We're going to hear a presentation from Dr. Sabbie Miller of the University of California, Davis, and then we're going to open up the floor for questions and answers. So we do encourage you to use the Q&A feature in the Zoom webinar platform. Go ahead and type in your questions at any point during the presentation, and we'll do our best to answer them. And we will be recording the webinar, and the recording is going to be available on our website along with the slides. So I'll make sure that that link is in the chat if you want to access that. So with that, let's go ahead and jump into our presentation. I'm very happy to introduce Dr. Sabbie Miller, who's an assistant professor of civil and environmental engineering here at UC Davis. Her research focuses on improving the sustainability of the built environment, including through more efficient use of cement in concrete and of concrete in applications and infrastructure, which we'll be hearing a little bit more about today. So Dr. Miller, we're so thrilled to have you join us, and I will turn it over to you.
Wonderful. Thank you so much for that introduction, and thank you for having me. So as was mentioned today, I'm going to be chatting about cement and concrete, specifically looking at strategies that can improve our utilization of cement and concrete, because in reality, we are oftentimes concerned about using these materials from the perspective of they can contribute to the production of greenhouse gas emissions, and that could lead to issues associated with climate change. But in reality, we actually end up seeing that these materials contribute to other environmental burdens as well. And if we could just use them more efficiently while still getting the same performance that's desired, there's this potential to actually have a significant reduction in multiple environmental impact categories concurrently. So with that in mind, I want to kind of give a little bit of an additional perspective as to why these other environmental burdens can be an issue as we look at infrastructure materials. And then, of course, we will focus on the carbon dioxide emissions as they link to cement and concrete production, because that is a primary concern associated with our high levels of demand for this particular infrastructure material. So if we think about infrastructure materials in general, we're usually using them because we need certain structures and services, and infrastructure materials facilitate our having those structures and services. In order to make our infrastructure materials, we end up needing a certain amount of resources and a certain amount of energy. And in reality, our structures and services also need a certain amount of energy. Also, though, we note that we need structures and services to support our energy resources and our access to energy resources. So there's a bit of an interfeeding loop between those two. And again, we start to see that, okay, infrastructure materials are not only necessary for our structures and services, but also a part of our meeting demands associated with energy resources. What we end up seeing, though, is that if we keep looking at these systems, they become a little bit more intertwined. If we think about what else has an associated burden with our production of infrastructure materials, well, there's a certain amount of particulate matter from producing infrastructure materials. There's a certain amount of greenhouse gas emissions, as I mentioned earlier, from producing infrastructure materials. There's certain waste flows. We don't have perfectly efficient systems when we're making our infrastructure materials. So there's going to be a little bit of solid waste, a little bit of liquid waste associated with any of our processes. And of course, the energy resources necessary to produce the infrastructure materials, as well as the energy resources we use in our other systems, also lead to greenhouse gas emissions and air pollutants. So again, the system becomes just a little bit more complex. If we take that another step further, we end up seeing that our greenhouse gas emissions, our air pollutants, and several other impact categories can actually contribute to human health burdens. We end up seeing that there's a certain amount of water consumption that's tied to our infrastructure material demand. Basically, we end up using water in certain processes, and therefore we end up having a certain level of consumption just to make the materials that we require. But then again, we also need infrastructure materials to facilitate the transport of water. And we end up seeing that there's other forms of contamination that can be associated with certain infrastructure materials, depending on how they're produced and how we maintain quarries, for example. Again, this is just an example. We do end up seeing pretty good maintenance of many systems. The issue here being that if we only look at infrastructure materials based solely on the performance that we're getting out of them, just exclusively on the structures and services, we could exclude by accident all of these additional burdens that are actually tied to the exact same materials. Or if we only focus on the materials themselves and try to improve the engineering of those materials, we might accidentally miss that we need to meet a certain performance requirement. We might engineer a very environmentally friendly material that doesn't actually meet the behavior requirements that we have associated with it. Similarly, if we only focus on a particular environmental burden, like greenhouse gas emissions, we could miss that there are other burdens associated with these materials. So ideally, as we're engineering our infrastructure materials, we should not only look at the performance characteristics for those materials, the requirements of the structures and services that we're actually engineering, but also a whole slew of different environmental burdens, such that we make sure that we're meeting mitigation targets without causing unintended consequences. And from that perspective, we end up seeing that the efficient use of those materials for meeting the same structures and services is one of the best ways to reduce overall demands, because if we don't need as much material, then we wouldn't have the additional burdens associated with them, is the theory behind that particular mentality. Now, of course, it's easier said than done, because we've actually started to see a pretty strong upswing in our overall materials consumption. And this is tied to several factors, one of which is there are more people, and people need infrastructure systems and services in order to have, the day-to-day lives that they would like to lead. So if you think about the number of people that accumulated, which is not the right word, up till 1900 Common Era, we end up seeing that up until that point, we only had 1.5 billion people living on the planet. From 1900 to 2000, there were an extra 4.5 billion people that were living on the planet. And those extra people, again, extra is not the exactly right phrase, but those people needed additional infrastructure systems and services. And of course, now we're over 7 billion people, and it's only been about 22 years later, and we have this additional burden associated with the fact that these people need systems associated with their individual consumption. So we have a drive affiliated with the population growth that we're seeing around the planet. In addition to that, we also have seen an increase in affluence in many populations. And typically when we have a population that has appropriate levels of affluence, they're capable of purchasing additional systems, which then leads to additional impacts. So you may have heard of an equation referred to as the IPAT equation. Basically, our impacts are a function of our population, our affluence, and the T is technology. So oftentimes, if our population is growing and our affluence is growing, we would see a rise in our impact unless we have technological breakthroughs that could allow us to meet those demands in a more efficient way, or with ways that lower the overall burdens associated with our materials consumption. Now, in particular, when we start to think about cement and concrete, this becomes even trickier because our consumption of cement has actually grown faster than many of our other infrastructure materials. This particular chart is showing you world production in terms of kilograms per person as a function of time, just looking over the past handful of decades. And we have on this plot wood at the very bottom, followed by steel, and cement is the top line that's plotted. And I want to note, of course, cement is just a powder component that we use in cement-based materials, concrete being the predominant cement-based material that we make globally. But we can't plot concrete on this particular chart because concrete's mass is about 7 times greater than cement, if you take into account the water that's necessary for the hydraulic reactions, and if you take into account the aggregates that we put into concrete. If I were to have plotted concrete on this chart, you wouldn't be able to see steel and wood. The lines would be so close to the bottom. So if we think about this just solely in terms of mass of consumption, we see that cement is growing faster than the other materials that we rely on for infrastructure systems, and it's a large amount of material that's necessary for the full engineering engineered concrete systems. Now, in terms of greenhouse gas emissions, this has started to raise a few concerns because we oftentimes see that the production of cement is tied to this dependence on the calcination reactions, the limestone decarbonation that facilitates our making a reactive cement. And that leads to not only the energy necessary for that reaction to take place, as well as the formation of calcium silicates, but also a chemical derived carbon dioxide emissions, the actual limestone decarbonation leading to emissions straight from that mineral resource. So these two factors together are actually leading to cement being one of the sometimes referred to as a little bit needing additional technological breakthroughs to mitigate carbon dioxide emissions. This particular chart that I'm showing you here is highlighting that particular factor, where carbon dioxide emissions associated with industry is being plotted, as well as our emissions associated with fossil fuels. It's not showing you emissions from agriculture, though, for example. And as you can see on this particular chart, there are many strategies that we have in place that could start to lower greenhouse gas emissions for many sectors. And those are the lighter colored chunks of this particular pie chart, are areas where we have technologies that could get us down to approximately net zero emissions. Whereas we have over here in purple, our cement is pulled out because we don't necessarily have technologies to get rid of the limestone decarbonation emissions. Now, I want to highlight here, to produce cement, we have this limestone decarbonation, but we also have energy inputs. The energy related emissions for cement production are actually buried in this other industry chunk. So while this particular pie chart indicates that cement is responsible for approximately 4% of our global carbon dioxide emissions, that's from the limestone decarbonation. In reality, cement is actually responsible for a bit over 7% of our global carbon dioxide emissions when you take into account the energy demands that have been buried in this other chunk. So if we now think about this one material resource that we are using more and more of as populations and affluence grow, it has carbon dioxide emissions associated with not only energy demand, but also the mineral resources that are utilized and the way the chemical reactions are set up to facilitate a reactive product. Together, combined with this growing demand for the resource, we are starting to see this be one of the key materials that we need to decarbonize in order to meet greenhouse gas emissions goals. So there's several strategies that have been discussed on this front. One is reducing the demand for these materials. If we can use these materials more efficiently, as is the goal of this particular discussion today, then we could lower overall emissions by basically pulling back on the consumption level. So yes, we would ideally also have technological breakthroughs in terms of how we use the energy resources, how we are dependent on these chemical reactions. But if we could just lower overall demand by efficiently using these resources, that will contribute to a reduction in emissions. We also have the potential to lower impacts associated with cement and concrete by re-engineering the existing materials intentionally to lower burdens. So basically, for those of you who are in the cement and concrete world, this could include things like mixture optimization and other improvements that are really looking still at the same cement and concrete, but basically tailoring it to mitigate environmental burdens, including things like manufacturing improvements, so more efficient kiln technologies, et cetera. We also could develop brand new materials that have comparable functionality and lower environmental impact. As you can imagine, when we're looking at an infrastructure material, this can get a little bit complicated due to how the supply chain and the value chain value and use this particular material resource. And in particular, with our infrastructure materials, there's this aspect of we need to consider what the material will do. We apply our cement and concrete and intend to use it for decades at a time. So if we engineer a material that leads to lower performance, that could not only be a burden in terms of costs associated with maintenance, replacement, et cetera, but it also could be a safety concern, which is absolutely not what we want to do, which is why I oftentimes show this cartoon when I'm discussing material performance. This is basically somebody showing a scientist, we've made your environmental report greener. It now uses 50% less paper. But as I tell my students, which of your professors is going to accept a report that has that particular cutout structure associated with it? That is not a functional piece of paper anymore. So we could extend that mentality to our infrastructure materials and basically say we cannot do any form of material efficiency or switching out for alternative material resources if it's going to compromise our ability to use this material in a way that's structurally safe. So linking this back now to how we can efficiently use our cement-based resources, I want to highlight again our cement consumption. This is now total production as opposed to per capita. And I'm showing you, again, the same time horizon as I plotted on the previous chart. The line is indicating our cement production over time. And as we built up our infrastructure systems, we had an increase in our cement production because cement almost exclusively goes to the production of buildings and infrastructure. Now, keeping in mind, again, cement is just one constituent of our cement-based materials. We end up seeing that when you look at a material like concrete or mortar or grout, in reality, there are other resources that are necessary. You have your cement, you have to have a certain amount of water to facilitate the hydration reactions. There's going to be a certain amount of aggregates, and actually these make up the largest volume of our cement-based materials. And in typical mixtures, you end up with a fair amount of air that gets trapped into the mixture. So as we're thinking about ways to engineer these materials such that we could utilize them more efficiently, there's a way to approach this that can kind of be categorized based on the life cycle stages of those materials. So what efficiency measures can be implemented at the manufacturing level? What efficiency measures can be implemented at the material level? What efficiency measures can be implemented at the structural design and use level? And then what efficiency measures can be implemented at the end of life level? Let's start off with the manufacturing level, since this is actually where we most commonly discuss re-engineering existing materials, and improvements in the manufacturing system often are discussed as among the primary ways to decarbonize our material systems. When we're thinking about cement and concrete, oftentimes we don't actually get too concerned about the greenhouse gas emissions associated with the other concrete constituents, the aggregate, the water, any type of chemical admixtures that are utilized, because relative to the production of cement, those other constituents oftentimes don't lead to very high levels of greenhouse gas emissions. Usually we're much more dependent on reducing our clinker within the cement to reduce greenhouse gas emissions. Now, let me take a step back and explain clinker. Basically, in order to produce our hydraulic cement, our conventional Portland cement that we use in bulk, what we need is a fair amount of limestone and actually clays as raw materials that are used together in order to form a compound that has these potential for the hydration reactions that facilitate the mineral structures that we need to hold together our aggregates and support concrete strength. The limestone itself, if you think about a limestone formed of calcium carbonate, we actually have to have that decarbonated to convert it into an equivalent of a lime. Basically, what ends up happening at that stage is there's going to be a certain amount of energy input for the chemical reaction to take place, and our calcium carbonate turns into calcium oxide. We have a certain amount of carbon dioxide emissions from that mineral resource converting its compound. And in addition to that, the calcium oxide is not the final stage. We actually have to continue kilning the material with silicates in order to form calcium silicates that are then used in our Portland cement. The kiln is actually operated at an even higher temperature than the limestone decarbonation, so we have additional energy input associated with that stage. We have some energy that's associated with cooling and grinding of the material. The material that actually comes out of the kiln is the clinker that I referred to just a second ago. It gets interground with other mineral components. Oftentimes we have gypsum to control the set of the Portland cement, but we're also seeing more and more intergrinding with materials like limestone, et cetera. And you end up with your cement that can then be used in the production of concrete. Now, these stages of chemical-derived carbon dioxide emissions from the limestone decarbonating and emissions associated with the cement kiln are what we see as the primary contributors to greenhouse gas emissions for cement and concrete. Basically, our quarrying activities for aggregates pale in comparison to all of these processes that we see for cement. So even though aggregates are by and large the main volume of our concrete, they are not the main contributors to greenhouse gas emissions. However, they are large contributors to things like resource scarcities and particulate matter formation at quarry sites, because it is the by volume larger component of what we're putting into our cement and concrete, our concrete namely, not into our cement. I apologize for that. So if we think about this from the perspective of, if we focus exclusively on decarbonization, we might actually just be pointing our eyes directly at this production of clinker, where we have all of these manufacturing stages that are resulting in greenhouse gas emissions. And we might completely exclude an analysis of a resource that's used in concrete that actually contributes a great deal to things like particulate matter formation, that contributes a great deal to things like resource scarcities. And as a result, we might not be paying attention to a full picture when it comes to environmental impacts. However, if we could use our concrete efficiently, we will able to lower our overall demand of these material resources and contribute to cumulative benefits in environmental impacts. Let's focus back in on those greenhouse gas emissions from cement production for one more second so we can get through this manufacturing methods as a way to mitigate burdens. We had this plot before of our cement production. What I'm showing you on this lower chart is our percent of global CO2 emissions from cement production over the same time horizon, where the solid line is the carbon dioxide emissions from that limestone decarbonation, and then the dashed line is the limestone decarbonation plus energy emissions. So this is where we see that we're at a little bit over 7% of our global CO2 emissions from just one material. Now, there have been many manufacturing improvements that have been proposed. These have included things like using more efficient manufacturing kilns, using alternative energy resources, and in fact, also using alternative raw material resources to potentially change the amount of emissions associated with limestone decarbonation. Depending on the strategy that's getting implemented, as well as the baseline, right? So how efficient was the technology when we started? There's a range of improvements that can be seen for the utilization of these different manufacturing methods. I have just a quick summary of a handful of these on this particular chart, where we're looking at things like changing the electricity source, the kiln fuel source, as well as the raw material resources. And then on the bottom, I have what would happen if there's carbon capture and storage just at the cement kiln. So it's not including all the other emissions that build up in the production of this material. And we do see that there's a huge potential to lower greenhouse gas emissions for the production of our cement. Now, again, though, this doesn't get us necessarily down to zero. So let's look at the next level of production in order to understand some more of these efficiency strategies. Namely, let's look at our material level. And the production, whoops, too many slides. In the production of our materials, we have the ability to use our clinker in the concrete more efficiently, right? So if our clinker is one constituent within cement, cement is one constituent within concrete, the majority of our CO2 emissions are associated with clinker. Let's figure out how to use that clinker more efficiently so we're still getting a high performing concrete without having this huge greenhouse gas emissions footprint associated with it. Well, we could start to improve our mixtures by optimizing the designs, improving aggregate gradation, and the utilization of supplementary cementitious materials. Supplementary cementitious materials are materials that could work with our cement in order to support the utilization of a material that has similar or oftentimes actually improved performance relative to our conventional mixtures, basically by having an additional reaction that takes place. So for example, pozzolans are a very common supplementary cementitious material. Pozzolans on their own aren't actually cementitious, but they can react with calcium hydroxide, which is a product associated with the cement hydration. And under the appropriate conditions, so appropriate moisture, temperature, et cetera, they can actually form more calcium silicate hydrates, basically forming more mineral structures that are beneficial in terms of contributing to compressive strength, contributing to durability of concrete, et cetera. So there are many different types of supplementary cementitious materials. These have been studied for decades. And this is a chart that's from the Portland Cement Association of how different supplementary cementitious materials can contribute to a whole variety of different properties. And they could actually be specified in a way that leads to desired enhanced material performance and reduces our overall demand for cement. As I mentioned, though, there are other ways to reduce our demand for cement, and these do include things like improved aggregate gradation. Certain chemical admixtures or surfactants can actually improve our utilization of cement. So there are ways to start to tune the concrete mixture itself to reduce the cement demand within it. Oftentimes, this does lead to an increase in some other constituent, for example, the supplementary cementitious materials, the aggregates, et cetera. So that is a bit of a balancing act. But if we're most concerned about greenhouse gas emissions, we can efficiently use our cement within our concrete mixtures. Of course, we could then look at our structural design and use stage to, again, start to understand how we more efficiently can use these mineral resources. And that can include a whole variety of things, such as within our reinforced concrete design code, we actually have a range of strengths and reinforcement levels that are considered appropriate for any given design. So we could pick a higher reinforcement ratio, a lower reinforcement ratio, as long as we're meeting our design code within the range of specified allowable reinforcement, we should be good to go. And what that means is that we can actually have a certain amount of variability in the greenhouse gas emissions of any designed member that actually still meets design code. We could specify a slightly higher compressive strength or a slightly lower compressive strength, a slightly higher reinforcement ratio or a slightly lower reinforcement ratio, and that may still adequately meet our design codes, but could have a significant effect on the overall greenhouse gas emissions of any given member. In addition to that, if we're able to use members for a longer period of time or full built systems for a longer period of time without high levels of maintenance replacement or their degradation causing an additional energy input, we could potentially lower our demand to have more mineral consumption associated with things like maintenance or replacement. So we actually see at the design and use stage, there's a fair amount of flexibility that could be used to lower environmental burdens. As very simplified examples, I have here a simply supported beam with a uniform load. And basically the concept that I'm trying to emphasize is that if we were to change the strength of this particular material, then we might need a higher cross-sectional area if it's low strength, or a lower cross-sectional area if it's high strength. Same thing can be said for a column. If we change the strength of the material, we already have a set height. The column has to hold up a building, for example, but we might be able to change the cross-sectional area if we are able to change the compressive strength, and that could facilitate our having a slightly different volume of concrete necessary. Same could be said for durability properties. So here I'm showing chloride ingress, where basically if we are able to get a material that has a lower coefficient of diffusion coefficient rather, then again, perhaps we could get away with a slightly different concrete cover, or perhaps not have to replace the material as frequently if it does have exposure to salts. So the mentality here is that we could potentially change the volume of our concrete necessary for any given application if we specify a different input in terms of the properties necessary. So just to show you that as an example with reinforcement, this is very highly simplified members that I'm showing. We have a concrete column on the top and a concrete beam on the bottom. In this particular case, I'm showing them with the same reinforcement level. But basically what I want to emphasize here is that it's 5 different concrete mixtures with different water to binder ratios, which are what are highlighted here, and different utilization of an SCM, in this case fly ash, since that's the most common SCM used in the United States. So a higher ratio of fly ash to cement for these mixtures here, slightly lower one at the other end, and 0 fly ash used in this first mixture. And what's interesting is what we would specify in terms of a desirable concrete mixture to minimize environmental burdens for a beam, mixture 2 or 3, actually leads to a pretty high emissions mixture for the concrete column. And this is associated with how the strength of the materials play into the volume of material actually necessary, as well as the role of the reinforcement on the overall cross-section of the member necessary. And we see that if we wanted to lower burdens across multiple members for a variety of loading conditions, we actually might have to compromise and not choose the lowest emissions material for any given single member, but rather try to analyze an entire system cumulatively to pick a material that will lower overall burdens. And then, of course, if you add into that durability will affect our environmental impacts, then we also have to take into account the impacts associated with maintenance, replacement, any changes in the material's performance on other emissions. So, for example, surface roughness in a road, or if the material loses thermal properties within a building. And so what I'm showing you here is a cartoon of our cumulative environmental environmental impact as a function of time, where basically at each of these time intervals, some change in material behavior occurs such that we either need to do maintenance or we need to do a replacement, et cetera. And with each of those maintenances or replacements, we have an additional environmental impact. Now, of course, if we're standing at time zero, we have a little bit of uncertainty associated with when exactly we'll have to do that maintenance or replacement, which is why I'm showing you a distribution on this particular chart. And of course, we'll also have a little bit of uncertainty associated with the environmental burden that's going to be associated with any given change, but we're able to still project outwards to get a sense of what the total environmental burdens will be for the life of this particular structure. And we could do that for a variety of different permutations of, well, what if we change the material design? What if we change some of our utilization impacts, et cetera? And we could pick statistically significant changes in how we're handling our materials to lower our environmental burden. So I'm showing you here, again, that there is uncertainty in this environmental impact, but we can pick a system that will have a high likelihood of driving down environmental impacts. Now, particularly what we end up seeing in terms of a change in our overall consumption is that the longevity of our structures can play a pretty significant role in ways to drive down our environmental impacts. What I'm showing you here is our cement consumption for different infrastructure systems and buildings, and we are increasing the longevity of those systems, assuming minimal levels of maintenance or replacement to increase that longevity. And we see that streets and highways in particular, if we're able to increase the longevity without having a large increase in maintenance and replacement, we could actually have a really significant reduction in the amount of cement necessary for those systems. So again, trying to understand how the longevity of that system will start to influence our overall materials consumption. There's also the potential to lower impacts at the end of life stage. In particular, what we can end up doing is using our concrete and our other hydrated cement systems to actually act as a direct air capture mechanism or act as a mechanism to offset our demands for aggregates. Specifically, our crushed concrete can be utilized as either an aggregate or backfill. This is already a relatively common practice, and that will potentially offset our need for more cement-based materials, or at least more virgin aggregates. We also can use our crushed concrete as a direct air capture source. Basically, by increasing the surface area to volume ratio of our concrete, we can facilitate carbonation, potentially occurring at a faster rate. Of course, it still needs to be under appropriate conditions, moisture, temperature, et cetera, exposure to atmospheric carbon dioxide. It can't be buried under other concrete, but that also can act as a mechanism that actually facilitates lowering of an overall environmental footprint associated with the material, as long as there isn't harmful leaching. And then, of course, there's always the potential to landfill the crushed concrete, but that typically is not the most environmentally desirable option. The other benefit that we end up seeing associated with our cement and concrete materials is that the really high level of consumption means that there is this potential to convert them into a carbon capture and utilization source. Basically, because we use so much cement and concrete relative to all of our infrastructure materials, if we could re-engineer cement and concrete to act as a carbon sink, this is going to be one of our largest potential carbon sinks and man-made materials that we have on the planet. So this is an active area of research, basically trying to understand which components of our cement and concrete can we use as a carbon capture source, such that we are mineralizing atmospheric carbon dioxide and removing it from basically the contributors to our climate change. Now, of course, I started this conversation off by saying greenhouse gas emissions are highly important, but we also see these other burdens, and efficient utilization of material resources could help us lower environmental burdens across many impact categories. So what I'm showing you here is, actually, this is supposed to be CO2 emissions. I do apologize, it's not greenhouse gas emissions. What we end up seeing for our contribution of all cement-based materials, so including transportation, the other constituents, et cetera, used in the cement-based materials beyond just the cement itself, we're looking at a little bit over 8% of our carbon dioxide emissions are coming from this one material that we use around the planet. These are global statistics that I'm showing you here. Close to 9% of our carbon dioxide emissions from this one material. In terms of our energy demand to produce our cement-based materials globally, we're looking at about 3% of our energy demand. We're looking at about 2% of our water withdrawals to go to this one material. And we're also starting to see pretty high levels of air pollutants associated with the production of our cement-based materials. And these include air pollutants that are predominantly from the fuel resources that are used, such as NOx and SOx, as well as air pollutants associated with the mineral processing. PM10 and PM2.5 are from the fuel resources as well, but we do see a fair amount from how we handle our quarrying activities and our grinding activities, et cetera. So with that in mind, we can start to pay attention to the fact that, yes, there is this carbon dioxide problem that we would like to tackle as quickly as possible, but there's also this additional resource consumption and health impacts associated with our air pollutants that need to be paid attention to, because those are going to cause more localized scarcities. Carbon dioxide emissions is a global problem. We are causing global climate change. Overconsumption of mineral resources, water resources, and local health burdens are local and regional problems. Those are going to harm populations that are the closest to any given overconsumption of resource or emission of an air pollutant. So with that, we could actually take a further step and start to understand which populations are getting impacted by these particular systems. And while this research is much more in kind of an early stage, we can start to look at where our facilities are located and try to understand whether or not they're going to be causing a disproportionate impact on any given population. What I'm showing you here is a shot of the United States Environmental Protection Agency's Environmental Justice Screen, EJ screen, which has ways of measuring demographic indices associated with the populations across the United States. And here I'm showing you production of concrete, wood, and plastic, three of our favorite infrastructure materials, and whether or not those production facilities are occurring in areas with high demographic index, which would be an indicator of a population with a lower income or a high level of minority population in the area, or whether or not the production of these materials is occurring in an area with a low demographic index. And we see that the vast majority of our infrastructure materials is in fact co-located with populations that have a high demographic index. Now, this doesn't necessarily mean that it's a high environmental burden on those populations, because again, the research hasn't been done yet in this area. It's something that needs to be done, but it's something to be aware of. If we know that we're producing these materials in populations that have a high demographic index, it's something that we should really quantify to make sure that we're not causing a disproportionate impact. So with that in mind, there are many research and development areas that require further attention. These include alternative mineral constituents. They include further work in this material efficiency realm. We also need a better understanding of guidelines and policies, particularly because we see that within our current policies and guidelines, our current codes, our current recommendations for the utilization of these resources, there's actually a fair amount of flexibility. We could start to drive down emissions right now with the technologies that we have, as long as we're picking the appropriate constituents for our concrete, picking the appropriate structural designs, and picking the appropriate end-of-life methods for these resources. So how we could start to encourage that movement when we already know the options that will start to lower emissions is really an active area that needs to be paid attention to. And then, of course, keeping in mind that how we engineer our concrete will also affect other sectors and other materials consumption is something that we need to also spend more time paying attention to, in addition to the environmental justice work that I just touched on a second ago. So with that, I wanted to acknowledge all of the support that has been facilitating this research, and of course my graduate students, because they are the ones doing this research. So these are my graduate students, Josephine, Allison, Patrick, and Elizabeth. And of course, thank you to the funders, and thank you to NCST for running this webinar. If you have any questions, I mean, obviously I'll be happy to answer questions in this particular webinar, but you could also shoot me an email. I have my email address up here. And on the next slide, I have all the references in case anybody actually wants to see an individual paper, but it's a wall of text. So I will not click on that unless I am told to. With that, I'm happy to take questions if we're ready for it.
Sounds good. Thank you so much, Dr. Miller, for that presentation. I think it's clear that cement and concrete sector is incredibly complex, but also incredibly important in terms of decarbonizing and trying to reduce environmental impacts from any number of realms, not just greenhouse gases. So we've got some great questions coming in. Just a reminder to please go ahead and use the Q&A feature on the Zoom, and you can enter those in. And we're going to move into that portion of the webinar now. So maybe I can actually kick off with a question of my own that's a little more overarching, which is, you touched on this huge menu of strategies from all different parts of the life cycle of producing and using and end of life of cement and concrete. Is there a particular strategy or kind of handful of strategies that you see as the most promising at this point, or is this really going to be kind of an all of the above approach to decarbonizing cement?
I'm of the opinion that it's going to probably be a combination of factors, but because there are so many options, I think that different regions can really tailor which options they use to best suit their individual needs, right? So if it's really difficult for a particular region to implement a new kiln technology because it's too costly, the upfront capital cost is just going to decimate something, then there is the potential that they could decarbonize through a variety of other strategies that are kind of paired together to offset the fact that they can't do this upfront capital investment. But I do think that it's going to be somewhat regionally dependent, and I do think it's going to be multiple things necessary at once to get us there in a timely fashion, right? Because we have a pinch of urgency.
Well, yeah, so maybe we can shift a little bit into how to do this. And so we have a couple of questions about standards, and I know in some of your research you've talked about performance-based standards versus kind of more prescriptive standards for design. I wonder if maybe you can talk a little bit about what performance-based standards are and whether you've seen interest in kind of moving in that direction, or what it might take to move in that direction, if that's important.
So I do think it could lead to some significant benefits, depending on, of course, the individual ability of groups to do so, right, to actually make that shift. So, for example, if we are prescribing a specific amount of cement or cementitious materials for a concrete mixture based on a per volume basis, then we actually could potentially be over-prescribing the amount of cementitious materials actually needed based on what the material needs to do. So if we're saying that for any cubic meter of concrete, we need to have 400 kilograms of cement in that, oh, sorry, I realized I do everything in SI units, so I do apologize to folks that use US customary. But if we're specifying a high level of cement, or even just a level of cement for a volume of concrete, but in reality, we could have gotten away with a lower volume of cement had we been able to utilize appropriate water to binder ratio, the use of some surfactants to improve dispersion of the cement, different types of particle fillers, a good aggregate gradation, then we could have actually, in theory, lowered our greenhouse gas emissions, required less of the most costly constituent of our concrete, which is typically our cement. But if we've already said, okay, we need to have 400 kilograms, then we've basically locked out this as one of our options to mitigate burdens. And it's not to say that there aren't other options, but in terms of using these resources as efficiently as possible, specifying that we have to hit a target of a certain cementitious content could really kind of cut out, again, several strategies of reducing overall burdens. That said, I am not the best person to answer how easy it is to implement, because of course there's going to be a fair amount of verification, bureaucratic inputs, et cetera, that are a little bit beyond my research scope. But I do know that this is a strong potential for certain applications to mitigate overall burdens. And of course, it's not appropriate for all applications, but it is really valuable for the ones that it is appropriate for.
I think we're seeing a lot of interest among this group, among the questions we're getting in terms of carbon capture in concrete, or carbon. I'm not sure the appropriate terminology is capture, storage, utilization. Can you speak a little bit more about kind of how developed some of those possibilities are? And there was one of the questioners talked about certain states, advocates are starting to push for procurement bills that are kind of setting calling for kind of cement with low carbon or the ability to capture carbon. So maybe you could just speak to some of those technologies.
Yeah, so there's a couple of factors to think about when it comes to CCS and CCU with our cement-based materials. CCS, carbon capture and storage, as it's kind of thought of in terms of capturing flue gas. As you can imagine, it's slightly more developed for the energy industry, since that was, I think, the primary or the initial audience for that particular technology. But the cement production facilities are actually uniquely adept to having that sort of technology associated with them, because the flue gas has a really high concentration of CO2 relative to the other flue gases that we would normally see from our industrial processes, including energy generation. Reason being that we use both energy resources, right, for the cement kiln itself, and that chemical derived CO2, which means that both of those together end up kind of getting shot out in the flue, and it's a higher overall concentration of CO2 because of that chemical derived CO2 from the limestone decarbonation, which actually means that in theory, the carbon capture and sequestration technology could operate even more efficiently with capturing CO2 from that higher concentration stream. That said, I'm aware that there's a handful of pilot plants that are trying out this carbon capture and sequestration at the cement flue. I fear I don't know the exact stages of how much progress those individual pilot plants have made, but I do know that they are starting to test out capturing CO2 at the cement flue. There's other aspects, though, of carbon capture that are often discussed with our cement and concrete. One is this carbon mineralization process that is inherently occurring with our hydrated cement, which is basically the fact that our cement materials carbonate as time elapses under appropriate moisture, carbon dioxide exposure conditions, etc. The fact of the matter, though, is that while we're using our cement-based materials, this process occurs really slowly. This interaction between our concrete, for example, and the atmosphere, the CO2 that's in the atmosphere. This is a function of a whole bunch of different things, including the fact that our atmospheric CO2, when you think about it from a carbon mineralization process, it's pretty low concentration. It's really high concentration when you think of it from a climate change perspective, but when you think about it in terms of how quickly concrete can actually react with it, it's a relatively low concentration, and the vast majority of our concrete isn't exposed to this relatively low concentration CO2. So in terms of using concrete as a direct air capture mechanism with this particular CO2, the atmospheric CO2, it's going to be much more functional at the end of life of concrete when we're able to crush it down and get a really high surface area to volume ratio and make it such that more of the hydrated cement can be exposed to the CO2 at any given time. But of course, then you can't stack it too high because you need to have all of your particle exposed, ideally, to the carbon dioxide. So that is another area of carbon capture that's oftentimes discussed in the cement and concrete world, is the fact that it can, in fact, react with atmospheric carbon dioxide under appropriate conditions. But we need to make sure that we understand the timing because it happens very slowly while we're using the material. So you could be emitting a lot to produce the material and not recapturing it until another date. The other aspects that have been discussed are a little bit more on the new technologies front, the carbon capture and utilization, and putting it into the cement and concrete at the beginning of the life cycle. So this includes some cements that are actually carbonate instead of hydrate. So cements that solidify by reacting with atmospheric carbon dioxide is the ideal case, but in reality, the vast majority of these cements need a really concentrated amount of CO2 to solidify. But folks are trying to figure out how to get CO2 to atmospheric CO2 to be that source of CO2 to solidify our cements. There are other technologies where some folks have been playing around with trying to create either mineral fillers from atmospheric CO2 through biogenic resources. So, for example, bacteria that can form calcium carbonates, et cetera, and some other pretty cool technologies in the area. I don't want to list them all since I fear we'll run out of time, and I also will forget some and embarrass myself. But there are many technologies that people are trying to work on how can we engineer the materials that we're putting into the concrete such that we're mineralizing CO2 at the beginning of the life cycle. But those technologies are a little bit on the newer end of things.
Great, thank you. Sounds like a lot in the works on that front then.
Yes.
Let's see. We got a question about to what extent you're aware of governments starting to kind of step in and set targets for or standards for reducing greenhouse gas emissions in the cement sector. So I wonder if you could speak to anything you're aware of, maybe here in California or potentially in other jurisdictions in terms of government starting to set targets for reducing emissions?
Yeah, I'm most aware of the cement sector in California and the concrete in New York. I believe that there are a couple of other places that are making movement too, though. So in California, we have SB 596, which is a bill that kind of sets a target for not only hitting zero emissions from the cement sector, but I believe there's an earlier, 40% reduction in a shorter time frame. I want to say 2035, but that could be a mistake. If you actually want to know the date, I recommend going to the bill because I worry that I've misquoted that one date. In addition to California having goals for mitigating all emissions from the cement sector, New York has a bill associated with mitigating emissions from the concrete sector. And I believe they're using, I want to say they're using environmental product declarations to help facilitate that. But again, I could be mistaken. It's been a little while since I read the bill, but I do know that they've moved forward in that front. And internationally, I haven't seen quite as much in terms of the policy, but there are many different roadmaps that are getting implemented either by industry or by governmental organizations that are targeting emissions reductions. Again, I'm not entirely certain about individual policies, but it is something that is being pushed on many fronts around the planet. Yeah. Did that answer the question though?
Yeah, absolutely.
Okay.
I do want to follow up because you mentioned some of what's going on internationally, and we got a question about. So when we were talking before the webinar, you had talked about how much of this, skyrocketing demand for cement globally is really being driven by these rapidly industrializing countries, outside of the U.S. and Europe. Have you seen that some of these practices that you've discussed are maybe are beginning to be implemented in countries like China that are, that have this astronomical cement demand in recent years that, maybe they've learned from some of our mistakes here in the US?
There are definitely some improvements that have begun to be implemented in areas that have been able to learn from what the U.S. has done improperly. For example, in China, the cement kilns are all extremely high efficiency. So we have kind of older cement kilns in the U.S. because they keep working for decades. So, we end up just using them for decades. But I know that the Chinese cement kilns are far more efficient. Also, what I've seen the data coming out of some Chinese universities is an indication that they're using a much higher level of mineral admixture in the cement itself. Now, in the United States, we're not prone to doing that because we like to give our concrete mixtures or the ready mix concrete producers a lot of control over the level of mineral admixture put into the cement. But it looks like a lot of the Chinese cement producers are doing that mineral admixture stage in the cement production, which is actually prevalent in many other countries as well. And they seem to be specifying extremely high levels of clinker replacement. So it's some technologies are definitely getting implemented, but I fear I do not know all of the ones that are getting implemented. And it seems, interestingly enough, that this concept of efficient use within accepted design code, so picking the right reinforcement ratio, picking the right strength, picking an appropriate longevity, or at least trying to, knowing that it's going to be decades away. That one does not get implemented as regularly. And it's kind of unfortunate because it's one of those things that we don't have to change the design code. We don't have to change how we're approaching structural engineering or transportation engineering or any of these other areas, pavement engineering. We just have to, also add in how we calculate environmental impact so that you're looking at both concurrently, making sure you meet your designs, and then also lowering the environmental burden at the same time. And that I'm not seeing as much internationally or here as I think is necessary. So yes and no in terms of other areas, learning from things that we've done wrong.
Got it.
Yeah.
You talked about how a lot of these strategies have pros and cons. Maybe they'll have the potential to reduce greenhouse gas emissions, but they might increase water use or increase, a different type of pollutant. Can you talk about some of the life cycle assessment tools that maybe you've used in your research or that are available to kind of, how policymakers or local governments kind of work through some of those trade-offs?
Yeah, so there are a lot of software packages that can facilitate these sorts of environmental impact calculations. The UC PRC, the UC Pavement Research Center, has the LCAP tool, which I believe is now available. That is specifically designed to assess pavements such that you could draw these sorts of comparisons, and they look at multiple environmental impact categories. So it's not just greenhouse gas emissions. I believe they use the Tracy Impact Scheme, which is the United States Environmental Protection Agency's impact scheme, so that you could look at multiple environmental impacts concurrently. Some folks have started to play around with the use of environmental product declarations for these sorts of comparisons. Those can be actually a little bit tricky if you don't know the exact scope and boundaries of those individual environmental product declarations. It's not that they're not useful, they're extremely useful, but rather if a different company is using a different data input, so one company is using their exact energy mix and another company is using the US average, then you could actually start to get kind of a strange comparison, because it might not necessarily indicate that you're going to lower emissions if you pick one over the other, versus that you have better data for one than the other. So there's a little bit of complexity there, still a valuable area. There are some commercial software packages that can be used for environmental impact calculation. A couple common ones are like SEMA Pro and Gabby. We also have our own concrete emissions calculator that we are planning on submitting soon as an open source tool, so that local governments can pick it up and adapt it for whatever their specific needs are. We really wanted it to be open source because we wanted people to know exactly how things were calculated and allow them to change factors that would make it more unique to their individual region. But of course, we have to go through the peer review process, so that's going to be a minute. But there are many different methods. And of course, if whoever asked that wants an individual, like detailed list, shoot me an email. I'm happy to send you a list.
Great, thank you.
Yeah.
Getting close on time, so maybe we have time for, this may be our last question, but we got a question about nanocellulose as a concrete extender and strengthener. I'm wondering if you could speak to that.
Oh, yeah. So it's an active area of research that many folks have been looking into, is the utilization of some of these types of materials as kind of almost as like a low level admixture. And by low level, I don't mean low performance, but rather it's not used in a high quantity like you would with a mineral admixture. It is not my key area of research. I have been helping out some folks with environmental impact assessments, but Professor Weiss in Oregon State, and actually Samaya Nasiri, who just joined UC Davis, they know so much more about that particular area than I do, that I would really feel much more comfortable deferring to one of them in terms of things like the changes in performance that you're able to get out of those materials and the benefits associated with them. There is a really high potential, though, to use them to tailor the performance of concrete and basically not need as much concrete. We've been trying to help out with some of those environmental impact calculations of understanding how we can much more efficiently use all of the other resources in our cement-based materials by making sure that we're tailoring appropriately with these types of nanocellulose. But the exact performance changes beyond that, I would happily defer to somebody who's a true expert in the area.
Maybe a topic for a future webinar.
Exactly, yes.
Great, well, we're coming up on time. There's a couple of questions we didn't get to, so I apologize for that. I did want to just let everyone know that I put a link in the chat to a survey. We'd love to get your thoughts on the webinar and what we can do to improve for the next time. We will be having another NCST webinar coming up toward the end of March that we'll be sending out details on soon. With that, I just want to thank our audience for attending and for your great questions and participation, and especially to you, Dr. Miller, for your presentation and all your really thoughtful answers. So thank you so much. And with that, we will close the webinar and let you all get on with your day. So thanks very much.
Thanks for having me.